All right, in this video, I'll cover some of the details associated with the airfoil portion of the lab. I'm also going to close the loop on the boundary layer portion of the lab assignment. And as a reminder, you won't be expected to discuss the details of the boundary layer, but you will be expected to understand the high-level concepts of the boundary layer and how it relates to flow speed in the wind tunnel. Now, you've probably seen a similar plot shown here that indicates a region of nice, well-behaved attached flow and a nice linear increasing CL versus angle of attack. The Shepherd's Hook curve in the upper region is indicative of flow due to flow separation. Now, due to several complicated phenomena that we won't really discuss in this class, our data looks a little different, and we'll show that on the next slide. Now, here's a look at our data. This is really the data from 2019, so the 2021 data will look slightly different, but we'll observe very similar trends. And this will give you an idea of what your plot of the lift coefficient versus angle of attack really should look like. Now, comparing this plot to the previous one on the earlier slide, you can notice a similar trend in the linear region, but the upper regions look much different compared to that nice, well-behaved Shepherd's Hook from the previous slide. Now, the steep drop in lift coefficient is indicative of leading edge stall behavior, as can be seen by comparing the different types of stall and their corresponding CL versus alpha plots shown on the right side of the screen. Now, these different stall behaviors have to do with different separation bubbles and complicated flow, and those bubbles moving across the airfoil. Now, in reality, this flow separation is very, very complex and something you'll explore a little bit more in your junior year and then into grad school if you're interested. Shifting gears slightly to look at the boundary layer aspects in order to close that loop related to the boundary layer portion of the assignment. Again, you're not expected to do the analysis of the boundary layer as I'm doing that for you, but you will be expected to understand these concepts. Now, you've been exposed to viscous flow from Professor Ma's lectures already, and in reality, viscous flow is very complicated in that it's simply out of the scope of this class. But we can discuss the concepts and observe the effects of viscous flow here. First, you'll recall from earlier in this assignment that I mentioned the boundary layer is a region of retarded flow, slowed flow due to the interaction of the flow across the surface. Well, here's some data to confirm that conceptual understanding that we developed at the beginning of this lab. Now, you can see in the left plot the thickness of the boundary layer at different locations moving backwards in the test section. The boundary layer thickness is really defined as the height above the surface where we observe 95% of the free stream velocity. Now, that's shown in the plot as the little stars. Now, I also plotted the height that corresponds to a velocity of 99% of the free stream velocity. You can see that as the little circles. In both cases, you can see the boundary layer is much closer to the thickness predicted by assuming a turbulent boundary layer, and in the 99% free stream velocity case, the data points nearly match up very well with the turbulent boundary prediction. Now, the plot on the right side of the screen shows a prediction of the flow acceleration due to this boundary layer compared to the actual measurements. Now, the actual measurements are indicated as blue circles, and if you really use your imagination, you can see a slight upwards trend in that centerline velocity as we move backwards in the wind tunnel. Now, it's difficult to be really confident about this trend because in reality, the uncertainty of these measurements is as significant as the trend itself. But if we ignore that for a moment, we can definitely see a slight upward trend in that centerline velocity. Now, the colored lines indicate a prediction of the centerline velocity using the boundary layer as sort of a nozzle in the test section. Now, you can see an over-exaggerated diagram of this in the inset image in the upper right corner, which is just taken from the lab assignment itself. Now, using the conservation of mass, we can predict the flow acceleration. The upper line, the green one, assumes no flow at all through the boundary layer. Now, in reality, we know this not to be the case. Some flow is going to go through the boundary layer. So what we did is simply put a scale factor on the amount of flow through the boundary layer. Now, in reality, this probably isn't a great approach because the flow is much more complicated, but it is a simple enough approach to observe the trends that we're trying to observe. Now, if we allow a higher percentage of the flow to essentially move through the boundary layer, we see an improved prediction compared to the real measurements of the centerline velocity. At an estimated 90% of the flow through the boundary layer, as indicated by the red points, we get a fairly decent approximation of the measured centerline flow. All right, so now let's direct our attention back to the CL versus angle of attack relationship, really using this year's data. So this is a portion of the 2021 data that I took down from the Google Drive location and plotted it. So looking at this year's data, we can see a fairly decent match to the NACA data that you're also expected to analyze as well. Now, in order to really compare our data to the NACA data, we need to ensure the Reynolds numbers are comparable. This is something that you're going to do, and you'll be able to determine that the airspeed that corresponds to the NACA data via the Reynolds number is given. But I'll tell you that right now that is a reasonable approach to compare our data to the NACA data. Now, one thing to notice is that our data tends to deviate from the NACA data really as the angle of attack starts to increase. On the next slide, we're going to use the boundary layer data and approach from earlier, and also the concept of flow blockage related to the mass flow due to the airfoil to make a modification to our data so that it aligns better with the NACA data and in reality is more representative of the true CL versus alpha that we would expect for this particular airfoil. So the plot on the left side of the screen, the plot on the right side of the screen shows the result of this modification. You can see that our data, after it's been modified, really matches the NACA data much better than after this modification than before, as you can see with the small inset picture in the center part of the lower part of the screen. So what did we do here? Well, we simply used conservation of mass to increase the local V infinity around our airfoil. Now, in practice, the V infinity term is supposed to represent the free stream velocity that's far enough in front of the airfoil that the flow isn't influenced by the airfoil or the object itself. Now, due to the relative size of our airfoil compared to the size of the test section, the flow around the airfoil is really accelerated in the vicinity of the airfoil. So using the V infinity as measured by the pedostatic probe, which is far in front of the airfoil, will ultimately result in a slower free stream velocity than the true flow around the airfoil. Now, we can estimate this flow blockage and hence the correct free stream velocity by incorporating the boundary layer thickness from the previous slides and also assuming that the airfoil forward prediction blocks a portion of the flow. Now, to be clear, this is a very crude approximation for some incredibly complicated flow, but the approach is easy enough to implement so we can see some of the implications of real wind tunnel testing, especially testing an object that's on a similar size scale as the test section itself. Okay, so incorporating these ideas, we can see that the effective CL versus angle of attack points collapse much better towards the NACA data. In order to help us understand really kind of what's happening almost behind the scenes here, and also to help with the potential quiz question, let's look at the CP equation and the plot of CP versus X over C to understand effectively what happened. Now, if we increase the V infinity term, the CP will essentially decrease for all of the CP measurements. This essentially decreases the area under the CP versus X over C plot, which directly relates to the lift coefficient. Now, keep in mind that since the CP is non-dimensionalized based on the flow velocity, we really shouldn't notice a significant change in CL for different airspeeds. And this really remains true for this approach as we see the medium and the high speeds produce very similar lift coefficients. So the red and the black points and lines are fairly similar, fairly on top of each other, until of course the red line starts to deviate due to the flow separation, which I mentioned towards the beginning of this video. Lastly, and I really can't emphasize this enough, that this is a very basic approach to account for some of the systematic errors associated with our particular experimental setup. A true, more accurate approach is fairly complicated and honestly probably out of the scope of this class. So I hope this video helps you understand the boundary layer and the conservation of mass flow rate, especially through the wind tunnel, and some modifications that we can make to our test data in order for it to represent reality a little bit better. Thank you.